Hello everyone and welcome to CSCI 343 Fundamentals of Data Science. Today we're going to be talking about data and distributions. So if you've looked at your assignments so far, which hopefully you have, you saw this example in R1 for data in the wild. And this is one of my favorite pictures of all times. I took this in front of my house. I have a leaky gutter. Specifically, that guy right there. And there's these weird decorative plant things that live in front of my house. They were there when I moved in, and I never had the heart to get rid of them. They're not hurting anybody. But the cool thing is that they act as sort of a real life, living, breathing analog plot of how leaky our gutter is. So when it rains, the water should go off to the side and shoot out into the yard, but it doesn't all the way anyway. And we can see that these plants are growing proportional to their proximity to this leaky gutter. And this is cool. If we look at this and do some quick and dirty statistics, so to speak, and just draw bars across the measuring like how big these plants have grown, we can flip those guys upright. And this begins to look like something that we've seen before, something familiar. In particular, it looks like half of that normal distribution that we've been talking about in some of our previous lectures. So the normal distribution is one of two distributions we're going to be talking about today. Or actually, one of several types of distributions we're going to be talking about today. So we're going to be talking about probability distribution or probability density functions, and also cumulative distribution functions. Now, the probability density or probability distribution functions are usually, this is a generalization, but for the most part, we can consider those to be the normal distribution that we've been talking about. So given some range of outcomes, what's the probability that an individual measurement you take will fall into a particular range within that distribution? And this is what we mean when we look at those normal distributions from our previous lectures. This relates to something called the central limit theorem, and we alluded to this a little bit earlier on, but effectively it's a nifty property of our probability density function. That the more data we collect, the more closely we begin to approximate that normal distribution, that bell curve. And because ultimately we end up approximating that, and that approximation gets closer and closer and closer to the overall population distribution, we can cheat a little bit and not collect as many samples as there are, say, in an entire population, and still be able to do some generalizations about the characteristics of that population. And going back, it was like our examples of plotting our raw data from studies and seeing as we collected more and more and more data, the distribution of that data began to look more and more normal. And if we took an infinite number of samples, or all of the samples within a population, we would get something that would very, very closely approximate our normal distribution. You can kind of think of this as taking a digital picture of something. So really, photography, I like photography, it's fun, is in itself a form of data collection. It's light data about the thing that you're pointing that camera at. Now, in the old days of analog cameras, you were limited by like the molecular structure of like the coating on the lens or on the films and those kind of things. Nowadays, most of our cameras are digital, and digital cameras are limited by resolution, so the number of pixels that you can fit onto that sensor. And this is a really great analogy, because really what you're doing is you're taking a sample at different locations in the field of view of that camera and using that to construct an image. And the higher the resolution, or the more pixels there are in that image, the closer that image approximates the reality of what the camera was looking at. So when we collect data and we collect some finite number of samples, we're taking essentially a digital image of whatever it is we're trying to measure, whatever it is we're trying to study. And so the more samples we can get, the better. But you also end up with the same problem, if you have an image that has trillions and trillions of pixels, one, it's going to be expensive and difficult to get a camera that'll let you do that. And also that data is going to be so large, it's going to be difficult for you to process. So, can we get the same, or at least similar information from smaller images? And how do we know when we've got enough data? These are all really good questions to ask. And I love this analogy here because it leads to an exercise that, frankly, we usually do in person in class, and it's a lot of fun. We're going to try it remotely like this and see how it turns out. But let's run with this analogy. Let's run to our next slide, and this glorious masterpiece right here. This, that's what, 4 by 5 pixels? This is a photograph. It really is. This is a photograph that I took ages ago, and it's glorious. What is it? Well, at this point, people start jokingly saying, like, well, I think I see, if I squint my eyes, I see someone holding a baby, or I see someone with a red light bulb or something like that. But the truth is, with these few samples, you can't tell what's there. It could literally be anything. It could very well be a car, or a person, or a baby, or a sandwich for that matter. See, you got your bread here, your tomato in the middle, and a gray plate on the bottom. You can justify calling this just about anything, and say, well, the data suggest. No, the data doesn't suggest. There's not enough data here to suggest anything. So, with that said, be very suspicious of studies with small numbers of samples. But the solution to any problem, of course, is to collect more data. Here's that same image, but at higher resolution. We can tell a lot more now. We can actually discern like shapes and things. We still don't know what the heck we're looking at, but at least now we know there's some sort of triangular shape in the middle. Some people have said, well, I think it's looking down like the front of a boat, or maybe it's a lampshade or something like that. Now, the only thing we can say with any certainty at this point is there's a triangularish shape in this image. Is it multiple things? Are the blackish parts the foreground and the white stuff just the background, or is it the other way around? We don't know. There's very little we can say about what's happening in this set of data at this resolution with these few samples. But if we collect more data, suddenly things start to take a little more shape. We can see colors that we couldn't see before. We can see what probably looks like something triangular, and it looks like it's being maybe illuminated from the side. So we're beginning to get more detail about what it is we're looking at. We still don't know what it is, but we're beginning to get closer and closer to that real-world representation of what the camera took a picture of. At this point, we still don't really know what it is, other than we probably have something. It does look like it's probably a triangularish object, and it's being illuminated by lights. That's still a ton more information than we had when we first started this exercise. So if we collect more data, things begin to get a little more clearer. And we see a more defined shape. Maybe there's some sort of railing or something out here to the side. It's still kind of hard to tell, but it's definitely getting to be a clearer picture. And really, even though we probably doubled the number of pixels from this in the previous sample, or previous set of samples, we didn't get a lot more information. There was a huge jump from that first to second image, though. So let's collect some more data. Still, we doubled the pixels again. Didn't really seem to help too much. Let's collect some more data. Oh my goodness. Now we kind of see something that makes sense. This is a space capsule. And actually, I didn't take this picture. This is actually a picture of me. That's me there in the little window looking out at the world. Man, never take me to a science museum because I turn into like a 4-year-old. I am into everything. This was at the Boston Science Museum ages ago. It was so much fun. Anyway, at this point, we can look at this picture, and it's still not true to life, If you look at the image here, we can't read the united part of United States. So that data is lost, effectively. We can sort of tell this says states, but the actual word united is still pixelated out. We can't tell what it is. So we don't have a true-to-life representation of what I actually saw in the museum. But we do have enough information to say what this picture basically is. And, if we look at the flag, The flag of the United States doesn't look right. It looks like the stripes are going sideways. But if you're not interested in that, it doesn't matter. You've collected enough information to tell what the overall picture is, a space capsule. But if we looked at this and took it at face value, say we were an alien from another planet and we didn't know what anything is, and we were trying to figure out what was going on in this image, we might assume that, well, the flag of the United States has diagonal stripes. Or that, we have some bizarre set of characters that doesn't even look like legible above states. So this could just be the States space capsule. We don't know. If we were to take this at face value, we might make those assumptions. So even though we've collected enough data to get some really meaningful information out of this picture, a lot of the more subtle details still aren't clear, even though we've got a ton of data. So the thing that I want you to take away from this is how all research, science, all analysis works. You collect enough data until you can get the detail that you're interested in out of your image or your data set or whatever. But you can only draw conclusions up to a point. Once you start trying to tease out very, very fine details, you could bump up against the resolution of your data and not actually be able to extract the meaning that you're trying to get out of it. So with most studies, you sort of get a broad strokes view of what's happening. It might not tell you the individual stripes, so to speak, of your flag. It might not tell you the individual words in your picture, so to speak. But you can get the overall image of what's going on. But of course, as you collect more and more data, you get closer and closer and closer to that real-world approximation. And so now here we are with, this is probably a 21 megapixel image, somewhere around there. And now all of the information that we wanted to get out of this, we can probably get at this point. So we can count the individual stripes on the flag. We can't see the stars anymore, or still can't see the stars. But we can clearly read the words that are written on the capsule. And the more data we collect, the closer we'd get to getting all of the information out of this image. But it's usually not feasible, and sometimes not even possible, to collect that much data on something you're trying to study. So we rely on this phenomena, this approaching our normal distribution as we collect more and more data to draw broad strokes generalizations about the thing that we're trying to study. So when we sample and measure something, we're always going to, well, typically, not always, but typically get closer and closer to that normal distribution. Looking back at our example from our previous class. So, what do these tell us? Well, they actually tell us a pretty good bit. It's a very quick way for us to look at our data and determine what the population average is, what the average variation in that population is. Is it skewed one way? Is it skewed another way? You can actually get a lot of information just by looking at the overall distribution of your data. But oftentimes we want to know more. We want to answer questions. We don't just want to describe the thing that we're trying to measure. We want to answer questions like, is group A different than group B? Going back to our academic honesty example from our previous lectures. So can we use these distributions to ask those questions? Well, the answer is, yeah, sorta. We need more than just our probability density function or our normal distribution. We need something to describe how much of a population falls within certain areas within our population distribution. And this is where we come to our cumulative distribution function, or our CDF. So our probability density functions are our PDFs, as opposed to our portable document format, and our cumulative distribution functions are our CDFs. This describes the probability that a value falls above some portion of our PDF. Now, this isn't terribly useful by itself. The CDF is pretty much only useful when used in conjunction with a PDF. So if we put these guys together here, we have something that looks like this. So remember, our CDF tells us the probability that some value lies above or below a certain point within our probability density function. And so, for instance, if we wanted to find the 50% mark, so where 50% of our population lies below a line in our distribution. This probably sounds familiar. This sounds like I'm talking about a median, and really it is. The 50% point on your CDF should define the median position in a normally distributed set of data. And if it's perfectly normally distributed and there's no like outliers or anything like that, this also describes the mean of your population distribution as well. So 50% of the population is going to lie on either side of that vertical line right there. So what you do effectively is you trace out where, or the probability that you want to have as your cutoff, and you trace that out to where it touches your CDF, and then you draw that line down through your PDF, and that'll show you where the cutoff is within your population distribution for the percentage that you're interested in. And, similarly, if we wanted to describe the 10% cutoff within our population, we'd find the 10% mark on our y-axis, trace that out to our CDF, and then draw a vertical line, and that defines the cutoff for 10% of our population. So we can say that 10% of the population is going to lie below that line, meaning 90% of the population is going to lie above that cutoff. Okay, Okay, come on, little computer, you can switch the slide. There you go. Now, this helps us in many ways. It can give us the ability to answer questions like, well, what's the likelihood that value X lies within a population, or is it something else or something different? And so for 90% of our cases, say we measured something that was said, we had a value of, say, -2. And plotted it here on our PDF and CDF, or marked it here on our PDF or CDF. There's more than 90% of the population lies above that. So it seems unlikely, improbable, that that value is part of the population. But notice that there is a tail here that stretches off. There's still the possibility that it could just be that that value was an outlier and was still a member of the population. So when you do statistics like this, you have to accept and understand that occasionally you're going to make false positive and false negative, have false positives and false negatives in your analyses. So if we reject something that's actually a member of the population, that's a false negative. We claim that it was a member of the or was not a member of the population when in fact it was. And when you're doing statistics based on probabilities within a population, you're almost always going to have these kind of problems. Similarly, you'll notice that as you skew off to the other end, there's an infinite amount of space out there on the other side of that cutoff as well. So if we had a value that was way, let me actually use my pointer, get it, there we go, way out here on our distribution, chances are it probably wasn't a member of the population, but using this 90-10 cutoff on our CDF and PDF, it might give us the false impression that yes, that person or that measurement was a member of the population that we're measuring, when in fact it wasn't. So in this case, we end up with something called a false positive. And this is a result of doing something called a one-tailed test. When we use our CDF and PDF in this way, we're trying to bracket and trying to restrict the amount of error in our conclusions, our estimates, our guesses about whatever it is that we're trying to measure. And so a one-tailed test is often not completely appropriate. What you want to do is use something called a two-tailed test. So if we found the 90% cutoff here and drew that down and used that in conjunction with our 10% cutoff, we would then isolate this central part here. Sure, we're going to have some false positives, we're also going to have some false negatives, but now we've bounded our test in between these two sections of our probability density function. Now the question I want you to ask here is what is the maximum confidence of this shaded area. Previously, we used 90% as our cutoff. So we wanted to include 90% of the population in our one-tailed test example. Are we still examining 90% of the population? We're still using a 10% cutoff on either end. The answer is no. When you use a two-tailed test, you're cutting off equal amounts on either side of that distribution. So in reality, what we have here is an 80% bracketing of the population. So we can say with confidence, or some confidence anyway, that 80% of the population falls in between this 90 and 10% cutoff. Now, understanding this is actually pretty important because this is effectively the theoretical foundation of most of the statistical analyses that you're going to end up doing over the course of your career. For instance, if you've done like t-tests or ANOVA or something like that, this is what's happening behind the scenes. It's looking at the correlation or like the interplay between these two distributions, your CDF and your PDF. Okay, so we've probably covered enough new material for today there, so we're going to stop our lecture. If you have any questions, please feel free to contact me or the class TA. And otherwise, stay happy, healthy, and safe. Take care, folks.